Okay. We are about to start the very last Zoom for Nuclear Chem, which means the very last tape for the whole year. Okay. Albert Einstein, you recognize his picture. He has a famous equation, E equals mc squared. And that actually has to do with nuclear chem, and we're going to talk about that a little bit now and discuss um, what that all means. E equals mc squared is a formula that stands for energy equals mass times the speed of light squared. The speed of light is a constant. It's a humongous number. It's approximately 186,000 miles per second. So if you can imagine a number as big as that, squared, a gigantic constant squared, times matter, that would equal energy. Now, what he showed us with this equation, and this is not simple math, this is not easy for normal people or even me or you to understand. But what this basically says mathematically and theoretically is that energy and matter are the same thing. Energy equals matter times a really big number. Or if you can take a little tiny piece of matter, you can multiply it by a gigantic number and it will equal a lot of energy. Energy is matter in a different form. Matter is energy in a different form. Energy, E, equals matter. This is almost weird. This doesn't make sense. Stuff is not energy. What we understand to be energy, the ability to do work. Stuff is what energy works on. It moves my car. This is a really weird theoretical thing. But from this theory, from this mathematics, came the idea that atoms could be split, right, to create enormous amounts of energy. And from from that equation and more of them, the idea that a nuclear reaction could occur, a nuclear explosion could occur, a bomb could be made, or possibly, and later it did happen, the idea of controlling this nuclear explosion could be contained in a reactor to produce energy comes from Albert Einstein. Albert Einstein obviously was one of the smartest people to ever live scientifically. He was also a pretty silly guy. He was pretty happy, played the violin, he rode his bicycle. He was pretty silly. And that's a really funny picture of him. All right, this is what um, Einstein's theory and then many other physicists and chemists got involved in, the idea of creating a chain reaction. Now, a chain reaction means you start it small and then it gets bigger, and the next cycle gets bigger, and the next cycle gets bigger and bigger and bigger, and it can keep going as long as you have enough fuel. Now, the fuel in this case is something called uranium-235. Uranium-235 is pretty unstable. Right at the very top of the screen in the middle, you can see a little N, a little neutron is blasted into that uranium-235, which makes it so unstable it immediately splits in half, the splitting of an atom to release energy. And there are many atoms that can be split. There's uranium-235 can be split in different ways, but in this example, a neutron artificially is shot at this uranium. This doesn't just happen, which is good because we don't want nuclear explosions happening everywhere. But a neutron hits this uranium nucleus and it splits the nucleus into krypton and barium. And also what comes out is a little bit of energy and 3 more neutrons. Now, that can happen. And if there's more unchanged fuel, if there's more uranium-235, because you add more than one atom to start with, those neutrons could potentially hit 3 more uranium-235s, and all 3 of them will split into 3 kryptons and 3 bariums, and then 9 neutrons and more energy. And this propels it forward. And if there's more uranium, then 9 uraniums can get split into 9 more kryptons and 9 more bariums and 27 electrons, and then more energy. And it gets bigger and bigger and bigger. And if theoretically, if reality, if you have enough of this uranium, this can cycle, get bigger, 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 bigger. And at some point, it releases so much energy, you can literally have a nuclear explosion. You can, gigantic amounts of energy comes out. Now, when we burn Bunsen burner gas, we have table I. 1 mole of methane will release 890 kilojoules of energy per mole, 890.4. Gasoline, the octane, is the second or third one down. It releases 10,000 kilojoules per mole. These are millions of kilojoules per mole. This is an enormously different kind of chemistry. This is not even regular chemistry, it's nuclear chemistry. This amount of energy coming out is not like burning a hot fire. This is like 10 pounds of uranium could destroy an entire city. And that's what actually happened when the Americans dropped the bomb twice in Japan. Boom, and a whole city literally burnt to a crisp, and so were all the people. This is a tremendous amount of energy that can come out of it. Now, this is called the splitting of atoms, or fission, F-I-S-S-I-O-N, two S's. We're going to split it. And strangely, even though there's something called the law of conservation of matter, that does not hold true, because this is not really chemistry anymore. This is nuclear chemistry. And the mass of the products is slightly less than the mass of the reactants. But even though it's a very, very slight mass change, you get to multiply it by the speed of light squared, which is a gigantic number. So this tiny amount of lost mass, this mass defect, is converted into gigantic amounts of energy, the splitting of an atom. Now, here are two different fission reactions. Both of them start with uranium-235. Both of them get hit with a neutron, but on some days it changes into barium and krypton. That's the daughter nuclei, and 3 neutrons come out with energy, and it cycles and cycles. Or on a different day, for reasons I don't actually understand why this would happen, a neutron could split it into xenon and strontium, and 2 neutrons come out. So I guess in a sense, this would be a somewhat slower reaction. Instead of tripling every cycle, it would only double every cycle, but it would still give off an enormous amount of energy. A few more cycles and it would kind of catch up to its equation on top. Now, in a fission reaction, a much larger nucleus is hit usually by neutrons, which splits them apart. But this is not natural. This is not normal. It's caused by a scientist, or many scientists. It doesn't just happen. You don't have to be afraid that this is going to happen in Vestal or Binghamton or anything like that. This does not happen by mistake, and it's not even easy to do. Even though I can tell you how to do it. Where are you going to get neutrons? Where are you going to get uranium? And where are you going to get enough? This is not anything to be afraid of right here, because it's not going to happen. And it's called artificial transmutation because it's not natural. Now, what splits out, the barium and the krypton, or the xenon and the strontium, those are called daughter nuclei. That's a vocabulary word, daughter nuclei. Often, usually, they are radioactive as well, and they will have to undergo natural transmutation. The extra neutrons that are released will propel this reaction along. So when 1 neutron splits the uranium, you get 3 neutrons in energy. Then 3 more split, you get 9. And then 9 more split, you get 27. And it gets bigger and bigger and bigger really, really fast. And every cycle, more and more energy is released until quickly, seconds, if you have enough uranium, you can have an explosion literally big enough to destroy a city. Now, number 80, in a nuclear power plant, after scientists figured out how to let this go and explode bombs, which is one aspect of nuclear power, they said, wait a second, can we control this? Can we control this so it doesn't happen bigger, and explode big? Can we just get it going a little bit and then keep it going and keep it going and keep it going and keep it going, releasing heat for a long time? Because maybe we can make energy that way. Maybe we can make electricity. If we can somehow control this nuclear explosion from getting out of control, so all the energy comes out in 2 seconds, if we can get it to last for a long time, we can use that power. And that's exactly what came out of all of this work that the scientists were doing. Now, this is almost an incredible photograph. This is a photograph of a nuclear explosion in the 1940s out in the Pacific Ocean. Now, when the bomb exploded on or maybe just under the water, so much heat is released, so much of the ocean literally instantly vaporized, that this gigantic rush of hot steam, because hot air rises, just flushes up, steam, hot, up, and it just gushes straight up. And as it gets further and further into the sky, it begins to cool down as it gets away from the heat. And all this steam begins to condense into clouds, but so much more water or steam is coming up that it just pushes it into what's called a giant mushroom cloud because of the shape. It begins to look like a mushroom. Those are giant battleships that I'm pointing to with the arrows. Those are literally giant battleships with soldiers and sailors watching this event. And somebody took this photograph from a fair distance away from that. Those ships are probably a mile or two away from that explosion. And probably a lot of those sailors were zapped with radiation, but things happen when you're in the Army and the Navy. But I wouldn't call it safe, but that must have been an incredible thing to see. Unbelievably powerful, unbelievably powerful. Now, another type of artificial transmutation is called fusion. Fusion is the opposite. Instead of taking a big atom and splitting it, this is you take little atoms and you squash them together. And there's a few kinds of this as well. There's a whole lot of splitting of atoms. There's a whole different set of processes. And here also, there's different kinds of fusion. We're going to just take a quick peek at two. Again, there is a mass defect. And this particular reaction, fusion, is 30 to 40 times greater in power than fission. So this is literally out of control. We can do certain types of fission on Earth, and the sun, because it's so big and it has such incredible crushing gravity and pressure and temperature at the center, it can do a different kind of fusion that we can't manage on Earth. We can't create the pressure and temperature to make it happen. Okay, but the sun, which warms us up for billions of years, it's gigantic and we have no fear of it ever running out in anybody's lifetime. It all runs on fusion. Simple, it's a very simple, we'll see it in a second, simple process. The sun will take 4 hydrogen atoms, basically 4 protons and 4 electrons, and squash them together into a helium atom and 2 electrons, quote unquote, or beta particles, because they're not electrons anymore. 2 beta particles come out and energy. And this happens over and over and over and over. 4 hydrogen atoms form into helium and 2 beta particles, and just tremendous amounts of energy come out. The sun actually is a gigantic ball of hydrogen, gigantic. And it's mostly hydrogen, but it's over time turning into helium. We have nothing to worry about. It should last billions of more years. There's nothing to be concerned about. But on the sun, this is possible. Now on Earth, we can't create the temperature and pressure to do that. There are, though, 2 kinds of radioactive hydrogen. One is called deuterium, H2, and one is called tritium, H3. Now, scientists on Earth have been able to take 2 kinds of radioactive hydrogen and smash them together to make helium and a neutron, and energy comes out. This is a different kind of fusion, small atoms squashed together into a big one. Now, this requires enormous pressure and temperature to do. And actually, the only way to do this is to put the deuterium and tritium, that kind of radioactive hydrogen, in a container, and around it, you build a nuclear bomb, like a uranium bomb. And when that explodes, that creates the pressure and temperature to be the trigger to make the fusion reaction happen. And when this happens, when a hydrogen bomb is exploded, this is enormously more powerful than the bombs that were dropped by the United States on Japan during the end of World War II. This explosion is wildly out of control and enormously bigger and more violent. And luckily, this is never going to happen by mistake. Hopefully, it'll never happen on purpose, as far as I'm concerned. Now, if we could possibly control this, and we can't control fusion, but we can actually have learned how to control fission, how does a power plant even work? Well, in Johnson City, you can still see an old one, still there. They only closed it a few years ago. You go down Route 17, just before you turn south on 201, on the right there, kind of across from where Wegmans is, there's a giant smokestack, and there's a giant building that used to burn coal. And the coal would come in by train. The tracks are still there. The coal would come in. They would burn the coal. The heat, and that's all you really need to make this happen, the heat would turn water into steam. Steam is pumped through a pipe, and it turns what's called a turbine. The turbine is basically a big fancy propeller, and the steam comes shooting through this pipe really fast because it's really hot and under high pressure, and it causes this turbine to spin like crazy. The turbine's connected to by like a metal rod to the generator, and the generator basically is just a bunch of copper wire and magnets. And when the magnets spin around copper wires, that actually creates electricity. Electricity and magnetism are very close, and when you get to physics, you'll see that there's a really big connection there. But spinning of magnets makes electricity as long as they're spinning around the electric wire, copper wire. And so anything that makes heat will boil water. Anything that boils water will produce steam. The steam will turn a turbine. The turbine turns a generator. And this process has been around for 100 years at least. All right? They've been burning wood. You could burn wood. You could burn natural gas. You could burn oil. But everything we burn produces poison in the air, carbon dioxide and greenhouse gases, and also acid rain and stuff like that. So it's not very healthy, especially if you live near these things. But all this junk gets in the air. It's really bad. If we could say, make heat without burning stuff like that, no carbon dioxide, no acid rain, that might be really cool. And that's pretty much what a nuclear power plant does. A nuclear power plant, very simply, is a controlled fission reaction. Hopefully you can control it. That's the plan. And basically it just doesn't get too hot, but it makes a lot of heat. The heat makes the water boil, makes the turbine spin. The turbine spins, and that turns into the generator. And that spins magnets around wire, and electricity comes through the house. The electricity you're using right now that pumped up your batteries or that you're plugged into right now to watch this video. In Oswego, New York, I used to live there. I used to go look at it because it's really kind of cool to see. There's a nuclear power plant up there, right on the edge of Lake Ontario, that makes energy by controlled nuclear fission. And some of the electricity we get right here in the southern tier comes from Oswego. It's really kind of cool, all right? It's kind of cool, I have to say. We'll talk about this. Now, obviously, this is not the plan for nuclear power plant, right? There's a million moving parts. There's many, many systems that back each other up. It's got a lot of safety features. But in simple terms, this is how a nuclear power plant works. We're going to start on the left in this pink area called the reactor. In that little reactor, which is pretty big as a room probably, that's where the fission happens. They have uranium in there. They're able to shoot neutrons at it to get it started, and then it runs. But into that reactor, they're able to push those 3 control rods. Now, there's probably a lot more than that, but this is a diagram. The control rods are made of certain metals that have an unusual property. They can absorb neutrons, which is a cool property to have if you need to absorb neutrons. So when your chain reaction starts producing neutrons, you need to slow them down because they're all going to explode into uraniums and make this explode. There'll be a nuclear explosion. You need to calm that down. So you push the control rods in, and they suck up some of them neutrons. So you get the reaction going, but you don't let it get out of control. You just get it going a little, and then you keep it steady, and it just keeps running, producing a lot of heat for a long time. It never gets wildly out of control. Now, in this pink zone around it, that's water. But the water gets incredibly hot, tens of thousands of degrees, and it gets pumped through as steam through this pink zone. Now, all this pink steam, it's super hot right here. It goes up towards what's called the steam generator, and it releases a lot of heat into the blue water. We'll get to that in a second. Then it comes back around, and then it gets reheated, and it goes up there and releases heat, and then it comes back around and gets reheated. That pink water gets very, very irradiated. It becomes radioactive itself. It's toxic, and it needs to stay away from people forever. That's important. Now, this is a simple little loop here, and I'm sure it's a lot more complicated. But basically, they have pipes of this superheated steam wrapped around big tanks of water. So the heat transfers into the water to produce very, very, very hot steam. Not quite as hot as the pink, but dang hot. And that steam goes through this steam line and then comes down and hits the turbine, and the turbine spins like crazy. Turbine spins the generator, which is the yellow box, and inside of the magnets, they're bigger than rooms. And those generators spin the magnets around wires, and it doesn't show it, but wires come out here, and the electricity comes to the house. Now, once the steam goes past the turbine, they try their best to cool that steam down back into liquid water, so that when it goes back in here, it's hot water, but it can absorb so much energy, take as much energy out of the pink as possible, so that this steam is superheated again, spins the turbines like mad, and then as it spins the turbines, it comes down, you cool it off again. So there's the pink loop of super hot steam that's all radiated water. That's bad. Then you have the blue middle loop that makes really hot steam that turns a turbine that cools back down into water, and that hopefully doesn't really ever get too much radiation in it. The final loop, this outside loop, all nuclear power plants have to be built on an ocean or on a big lake, or they have to have access to a lot of water for these cooling towers. And what happens is the heat that's absorbed by these cold water pipes, the cold water comes in, the heat from the steam after it hits a turbine is sucked into these pipes, and the hot water is pumped out. And out of these cooling towers, you often see white clouds coming out because literally it's steam, hot water, just water, H2O, but it's really hot and it's steam and it comes out the top, and that's a waste product. Heat is a waste product of a nuclear power plant. Now, this water should not be any radiation. It is really hot. It does turn to clouds. It does cause a little more rain, I suppose. Sometimes they don't have cooling towers. Sometimes they actually pipe in really cold water from the middle of Lake Ontario from a couple of miles out. And then there's the pipe that goes back out. And a couple of miles out, they pump out hot water. And environmentalists don't really like that. I mean, hot water does disrupt the ecosystem there. But if everything works right, the only real waste product is hot water and the fuel that gets used up, which we'll talk about later. So hot water, so there's 3 loops. We'll go through these again. Now, the pink is inside a giant construction of concrete and steel that hopefully, if anything bad happens in there, will stay in there. And that stuff's really bad and really toxic. In Russia, during the Chernobyl meltdown, they couldn't get the control rods in. It overheated, and it literally melted through the containment, and all that stuff went into the air, and it really poisoned much of Northern Europe and a lot of Russia. Really bad, lots of toxic radioactive gases and liquids, and the water, everything just goes in the air, and then it just rains down, literally comes down with the rain. So hopefully all that stays in there forever. That's the general plan. Now, the reaction should start a very small nuclear explosion, but it should not get out of control. Control rods should control that, and there is going to be equals mc squared in there. There is going to be a slight loss of mass that's going to be converted into energy. That energy is going to make steam. The steam's going to turn the turbine turns the generator, and heat comes out the end and electricity comes out the wires. If everything works well, everything works well. This is a fantastic scientific device. This is really cool when it works well. Now, when it works badly, it's a total disaster. But usually, honestly, they work well. And when they don't, they really work badly. So, water in the pink pipes. It's really steam, superheated. Hopefully, it stays inside forever. Water in the blue loop in the middle. That water can get a little irradiated after time, but usually not so badly. And that's what is turned into steam also to turn the turbines. And then finally, we have that third loop, which is just for cooling. Hopefully the red water stays in the red and never escapes. The middle water should be okay. And then the outside is just hot water, literally hot water. That's, somewhat bad for the environment, I suppose. It changes the local ecosystem some. Now, there's just another little picture. Steam goes out the top. And this is kind of a generic little plan. You want to go build a nuclear power plant. This is how you do it. You got to get a reactor on the left. You got to pump the steam through it. In this case, it's red and really hot. The control rods control the rate of reaction there of the nuclear explosion. Then there's the steam generator, which turns the turbine, which turns the generator, which actually here shows it's connected to wires that light up the city. That actually looks like Seattle. Looks like the big eye over there, whatever they call it, the Seattle Needle. And then the very bright blue here on the bottom right, that's just the cooling. It goes to a cooling tower, or maybe it goes to a lake or an ocean to get the heat out of there, because it's really big heat transfer system. The heat from the radiation makes steam. The steam heats water to make steam to turn a turbine, and then Finally, cold water cools that steam down, and then we pump out some hot water as a waste product. Now, you can read this all. Basically, it's everything I just said. Now, there are pros and cons to nuclear energy. We'll start with the pros. There's a lot of good stuff about nuclear energy. We don't burn anything, so there's no carbon dioxide, there's no greenhouse gases, there's no global warming, there's no acid rain. This is really good. We have a big problem with that, and nuclear power does not do that. It's consistent and reliable. It pretty much works all the time. Occasionally, it doesn't work. Once in a while, 3 problems I can think of, maybe 4, where it was a disaster, complete disaster. But mostly, it works pretty well, and it works 40, 50 years long. They last a long time. Many countries that get this don't have to buy as much oil. They don't burn as much stuff, which is good. Also, they're not economically at the whims of countries that might decide they don't like them. So economically, this allows them to become energy independent. Now, it does cost a lot of money to build one of these things, but once you build it, it kind of runs for a long time, and it doesn't really have as much expense as burning coal or burning a lot of other things. It's fairly low maintenance. You set it up and it runs for a year or 2, and you clean it out and you run it for another year or 2. It's not a lot of work. You got to watch it, of course. Now, there are cons to this also. There's bad stuff, nuclear power. There's radioactive stuff. Radioactive waste is produced. Every year there's radioactive waste we got to put somewhere. Now, the radioactive waste is going to be radioactive sometimes for 20 or 30,000 years before we only have half of it. So if you could figure out how to make that go faster, we can get rid of this radioactive waste, which is a serious problem, because what the heck are we going to do with it? Also, there are bad people that want it. They won't be able to make an explosion, but they could take this radiation and throw it in Central Park or on Wall Street or in London or anywhere and create terror, right? And it's very expensive to clean up. People got to get in the fancy suits and they'll pick it up. But this stuff is toxic to people. It's toxic for a very long time, and bad guys want it, and they'll want it for a very long time. So you got to find a place that's safe, keep it out of the environment, protect it, and you can't forget about it. Now, to get the uranium, it's expensive to mine and refine it, right? It doesn't come concentrated like copper or gold you could actually find in a vein, they call it. This takes a long time to get it. The disposal is a complete failure. We'll talk about that too in a little while. When there's a disaster, there's really a disaster. In Japan, the tsunami destroyed many nuclear power plants and caused a lot of radioactive waste to get into the environment. In Chernobyl, it actually melted down. That also is a disaster. This is talking billions of dollars of cleanup. Many people could get sick and or get cancer from this exposure to radiation. It's really bad. There's also a fairly high cost, a couple $1 billion to build one, right? There is a limited availability of uranium. And once you can build nuclear power plants, you can also divert some of this stuff and start building nuclear weapons, which potentially could make the world less safe, because there are countries that are a little bit more crazy, and they may decide to build a nuclear weapon. And if people use nuclear weapons, they're really destructive. I mean, America did it. America is the only country that actually launched nuclear weapons against another country, and they're very, very destructive. And honestly, now they're much bigger than the ones we even use. Now, here's a nuclear power plant picture. There's also a Nobel Prize right here. When nuclear waste is produced, it's radioactive, its temperature is hot, it stays hot for a long time, and we don't know what to do with it. We literally don't know what to do with it. Where are we going to put it? Nobody wants it in their backyard, literally. Nobody wants to have it drive through their town to go to somebody else's backyard, because if the truck falls off a bridge or is attacked, all that waste is going to be where you are. That's bad. So the plan right now, this is the plan. At every nuclear power plant in the world, they build a fancy swimming pool like this. And when the nuclear power plant needs to be emptied, when the fuel is used up and all that's in there is the bad stuff, they get the robots out, they go in there, they get the nuclear waste out, they put it in a container, they put that container into another container, put that container into a plastic container, and they put that container in the swimming pool that they keep pumping cold water in through to keep the temperature cold, and they're waiting for you to figure out what the heck to do with it. And honestly, I have to almost say I'm sorry. I had nothing to do with this, except people my age have been using nuclear power for a long time, and we all casually kind of like overlooked. What the heck's going on with this? Nobody normal knows what's going on with this. And even people who know what's going on, I don't know what to do with this stuff. I can't make them stop making it. We need it. But this is the plan. They put it in the swimming pool. Now, in Japan, when the tsunami came, they knew it was coming. They pushed the control rods in. They shut the nuclear power off. That part worked great. But all the swimming pools filled with this nuclear waste, when the tsunami hit and all the electricity went out and all the backup battery power went out, the water in these pools was not getting pumped anymore. And the water got hotter and evaporated. And then these containers started melting, and all this crud literally leaked out of the containers and into the air and into whatever water was around and exploded up out of the buildings. This is bad stuff. And this is the plan. They build a swimming pool for it. And when they need, they build another swimming pool for it. They're hoping you're going to say, this is a really cool idea. I got to figure out how to make this go faster, make the half-life shorter, win $1 billion overnight, right? And a Nobel Prize. Or figure out where we can put this stuff. There's nowhere to put it, but figure it out. That somebody's got to help us, because this is building up literally all over the world. Now, we're going to stop right here, and then we'll do one more video after this because it's too long and I cannot, I'll do it right now, but we cannot keep going.